Welcome! Today we are looking at a fundamental shift in high-performance computing architecture. The document at hand, the Photonic Blueprint, details a system called Chakra, developed by APIC Corporation in 2015 for an IRPAA study. As engineers, we know the industry is hitting a wall with copper-based interconnects. Chakra represents a move toward a general-purpose HPC architecture that replaces traditional chip-to-chip and board-to-board copper with a chip-level CMOS-switched high-bandwidth photonic fabric, what we call integrated silicon photonics, ISP, also known as heterogeneously integrated photonics and electronics, or HIP-E. By integrating a silicon photonic interposer directly with the CMOS chip, Chakra achieves a target bandwidth of 3.2 terabits per second across 64 channels. This isn't just an incremental upgrade, it's an architectural breakthrough on how we transition from distributed memory to a scalable, cache-coherent, distributed shared memory model to unlock true exascale capability. The physics of our current trajectory is unsustainable. Data movement energy is now the dominant constraint in computer systems. As this graph illustrates, copper loses efficiency rapidly beyond a mere 5 millimeters. When we look at the requirements for reaching exascale bandwidth, roughly 4 terabytes per second, using current copper and active optical cable technology, would require 1,792 watts just for I/O. That exceeds typical cooling capabilities by a factor of 10. The chips would literally melt. In contrast, by using HIP-E, we can deliver that same 4 terabytes per second bandwidth at an energy cost of just 21 watts. We can no longer simply scale up existing designs due to the physical constraints of pins per package and thermal limits. We must change the medium. Traditional HPC systems rely on distributed memory, DM, which works for highly localized tasks but is crippling for modern, low-locality data like Graph 500 or big data analytics. In a DM system, moving data from a memory node to a processor node incurs a massive latency tax, roughly 5,000 nanoseconds. This is comprised of 2,000 nanoseconds of software message passing overhead and 3,000 nanoseconds of hardware routing. Because of this latency loop, state-of-the-art DM systems run data-intensive workloads at just 11% efficiency. Chakra's goal is to eliminate this tax by moving the photonics from the I/O system directly into the memory system, providing a low-latency interface that makes remote memory feel local. Chakra is designed as a general-purpose high-performance computer built on 3 engineering pillars. First, it uses a standard 64-bit ARM instruction set. This is critical because it ensures a highly productive software environment that can leverage a large existing base of software. Second, it implements a new fabric that bypasses the limits of electricity. By using an integrated silicon photonics engine, we deliver high bandwidth and low latency across massive data center architectures. Finally, it uses advanced 2.5D and 3D packaging to prevent I/O bottlenecks. The result is a system that can scale from 2-socket servers all the way to petascale and exascale nodes without the traditional penalty of distance. The first pillar is the ISP engine. Our primary metric here is energy per bit. Chakra achieves 0.66 picojoules per bit, which is 75 times lower than current technology. By replacing copper with wavelength division multiplexing, WDM fiber optics, the energy required to communicate across a massive data center becomes identical to communicating across a single chip. We use 10 wavelengths per fiber, 8 for data, 1 for ECC, and 1 for the clock, achieving 224 gigabits per second, or 28 gigabytes per second, per fiber. Note the componentry. We utilize a disk modulator with a tiny 5 micrometer footprint. Because we use single-mode fiber with extreme low attenuation, 0.25 decibels per kilometer, our signal integrity and reach are entirely independent of the data rate. To realize this, Chakra utilizes a proprietary patented photonic multi-chip module, or MCM. This architecture successfully mates 28 nanometer CMOS logic circuits with an underlying photonic plane. The stack includes a silicon-on-insulator (SOI) wafer at the base, followed by silica optical waveguides. The CMOS signals are received by electrical interface circuits and then modified by optical drivers into light signals. This heterogeneous integration allows us to build the CMOS chips in any standard fab while bonding them to a specialized photonics layer using fine-pitch micropillars, ensuring high-bandwidth electrical connections between the logic and the photonic components. Pillar 2 is the architectural shift to cache-coherent distributed shared memory, CCDSM. By utilizing the massive bandwidth of the ISP fabric, we can drop global memory latency to under 100 nanoseconds. At this speed, all memory in the system, up to a 1 petabyte global DRAM pool, acts like local, on-chip cache. This eliminates the crippling software overhead of message passing entirely. A single load or store instruction can reach the entire global memory system instantly. This flattens the data center, moving us away from siloed memory nodes toward a unified, high-speed addressing space. The third pillar addresses the physical density required to support these speeds. To prevent I/O bottlenecks, Chakra relies on a 32-core CMOS processor plane integrated with 3 DRAM stacks. These 3D stacks provide 10 times more memory bandwidth than standard components with a staggering 15 nanosecond access latency, that is roughly one-third the latency of DDR3. This high-density logic and direct pin interface allow photonic data communication to reach the VLSI chips directly. This approach drastically improves swap-C, size, weight, power, and cost, by reducing the physical footprint while simultaneously supporting the high cache miss rates common in low-locality, data-intensive applications. Let's look at the hard numbers comparing Chakra's CCDSM to the IBM Sequoia DM system, mapped against a 1 million core configuration. The link bandwidth is 28 gigabytes per second, which is 38 times higher than Sequoia. More importantly, the bisection bandwidth is 26,000 terabytes per second, a 498-fold increase. This massive bisection bandwidth virtually eliminates congestion in the interprocessor chip interconnect. Finally, the global memory latency is reduced from 5,000 nanoseconds down to less than 100 nanoseconds, a 50 times improvement. These are the parameters required to move beyond the limitations of current supercomputing. Because Chakra allows applications with essentially zero locality to execute efficiently, shared memory inherently outperforms distributed memory for massive graph problems. Preliminary simulations indicate that Chakra CCDSM is 18 times faster than standard DM for data-intensive graph 500 type applications. If you look at the graph, you'll see Chakra, represented here as HIP-E with CCDSM, pushing the boundaries of both performance limits, measured in edges traversed per second, GE-TEPs, and power efficiency simultaneously. We are moving from the small data cluster of Xeon and Xperia chips into the high-efficiency big data quadrant. Unlike commodity commercial off-the-shelf processor chips, the Chakra architecture scales without the traditional penalty of copper distance. A single petascale node can house 1 million cores and 2 petabytes of DRAM. This entire system is contained within an 8 cubic meter physical footprint. This specific physical density is a design requirement. It ensures the round-trip speed of light propagation delay remains exceptionally low at 37 nanoseconds or less. By keeping the physical reach short, maximum fiber distance of about 8 to 9 meters, we maintain our 100 nanosecond total latency goal across the entire million-core fabric. These claims are not theoretical. They are the result of an IARPA feasibility study. APIC used a heavily modified modeling and simulation pipeline, including SniperSim and the Lawrence Berkeley National Laboratory co-design for Exascale Codex toolchain. We tested across various vehicles, including ARM, RISC-V, and x86. The validated outcome of these simulations is that fabric links can successfully demonstrate sub-100 nanosecond latency between randomly selected pairs of processors and memory arrays spanning up to 9 meters. This confirms that the switch logic, the photonic timing, and the CCDSM protocol are all viable for a target CPU in silicon. In conclusion, APIC's Chakra architecture transforms the economics of big data problem solving. By breaking the copper bottleneck and eliminating the software overhead of distributed memory, we deliver a system with 1/20th the energy consumption and 1/20th the cost of state-of-the-art systems, while providing a 20 times leap in performance. We are effectively eliminating the 89% efficiency loss currently experienced by supercomputing centers on data-intensive workloads. The future of the data center is photonic, and Chakra is the blueprint to get us there.